if set of t is the curve from this point, set of A, to set of B, the curve or arc if you like, then the derivative of set with respect to t can be written by this definition. Lim as delta t goes to 0 of set of t plus delta t minus set of t over delta t. This difference may be considered as some vector from this point, set of t, to this point. So taking the absolute value of this difference gives us the length of this distance. And if we add all such length, then we get something which is very close to the length of the curve length from this point to this point. So let's consider the summation of all delta set, which is this difference for a given delta t. And delta set over delta t multiplied with delta t is the same as delta set. So this is approximately equal to the derivative, the absolute value of the derivative of set with respect to t. Multiply, of course, with delta set. So this part is now, if we compare with the definition of the derivative, it's approximately equal to that for small delta t. And of course, this is only the case when the curve or the arc is differentiable. So that means that it's a smooth curve. We should come back to this afterwards. But now we also have to know that the summation of small elements like this, when delta t goes to 0, is this term is converging to the integral, this integral, as delta t goes to 0. And this is the arc length of the curve. Let's recall that the derivative of the curve can be written as the derivative of the real part of the curve plus I multiplied with the imaginary part of it. So taking the absolute value of this is, we note that it's equal to the square root of the square of the derivative of the real part plus the square of the derivative of the imaginary part. So the curve length L is just given by the integral from A to B of this integrand. As I told you, set of t is called a smooth arc if the derivative of the curve set of t exists at every point, and that it's not only exists but it's continuous. Moreover, we assume that the derivative of set with respect to t is different from 0 for all t between these two constant values a and b. And the reason for this is that we don't want a situation, for example, when, let me show you, if we have this curve here, when t is increasing, that we are going along the curve, but on some point we go back. We don't want this situation. So this would happen if the derivative of the curve is 0 at any point. So we avoid this situation by assuming that the derivative is different from zero. Another concept which is interesting and necessary for us to use is the concept of contour. A contour is an arc consisting of a finite number of smooth arcs joined end to end. So let us just give examples of this. Here is just a smooth arc. Here is a contour. It consists of two, in this case, two smooth arcs which are joined together in one point. So it's not discontinuous. So here we see a curve. Let's call this curve C. We often denote the curve, call it something, and C is a usual name for a curve. So it's defined by some function, some set of t from A to B, where t is from A to B. And now we are going to consider the integral of some function, complex function, f, along such a contour. What does this mean? Often we write the integral in this way, and on the lower part of it we use this as an index to indicate that we are integrating over the curve. And often we write from set 1 to set 2 if this is the point where set of A, and this is the point set of 2. And if the integral is independent of the path from this point to this point, we often use this notation for the integral. We have not yet defined what we mean by the integral, but we are going to do so. So the integral here, defined in this, written in this way, is defined in the following way. It's defined as the integral of the following function. We take f, the function f, and instead of set we write set of t. Multiply this with the derivative of f with respect to t, and integrate with respect to t. So this is the definition of the integral. This symbol, when we are writing instead of c under the integral sign minus c, we mean that we are integrating along the opposite curve. So we are not starting in the point A, but we are starting in the point B and go back to A. And it's possible to show that this integral is exactly the same as the opposite integral if we just put minus in front of it. This curve is used when we are combining two curves, C1 and C2, and want to integrate along with it. Then we write this symbol for the joining of these two integrals, and these two integrals are we write this new c in this way, and this means that we integrate over the curve c1 and continue with the integral over c2. Let's say some words about the absolute value of the integral over c. As defined earlier, previously we found that we mentioned that this integral means this integral with respect to t, and we have shown you an inequality earlier which stated that the integral of the absolute value of some integral is less than or equal to the integral of the absolute value. So using this and now using that the function f is less than some constant m, let's write this, we say that the absolute value of the function f is less than some constant m on the curve c. If this is the case, then we have, using this inequality I showed you, we obtain that this value must be less than m, using this here, and this m is a constant, so we can take it out of the integral sign and obtain this. But this is just the curve length from A to B, which is equal to this, we call it L, the length of the curve. So this inequality is often used, and we will use it later on in finding special integrals.